Hey learners, Jared here, and today we're going to investigate a little deeper into waves and how waves actually interact with each other and create some really cool effects, but we're going to focus on those particularly standing waves. Now, waves are, again, traveling energy, and energy can't be created or destroyed, again, neglecting nuclear reactions. Hopefully we don't make any of those in the classroom. So when one wave meets another wave, this isn't a joke like when one wave walks into a bar, he's always saying hi or something. But when one wave interacts with another, that energy adds together algebraically. Now, you can effectively cancel out a wave where that energy is still there, but you just can't see it. So for instance, if I have the peak of one wave traveling and it meets the trough of another wave, those two amplitudes will cancel each other out at the point where those two waves meet. Now again, that energy isn't gone because the waves will just travel through each other as if nothing happened, but at that point where they are actually superimposed or on top of each other, their amplitudes will add together algebraically. Now this works for destructive interference like what we just saw with a peak meeting a trough, but it can also work for constructive interference, where the amplitude of one wave, positive amplitude, let's say, meets positive amplitude of another wave, and those two waves will add together to give you a bigger wave. Now, let's say instead of a singular peak or a singular trough, we actually have a series of waves traveling along, and they meet another series of waves traveling along. If their frequencies are right, those two waves can interact with each other to generate what's called a standing wave. That is a wave on string or in air that appears to just oscillate up and down and not actually look like it's traveling anywhere. So let's start with just waves traveling along something like a string. Key factors that are going to affect whether a standing wave can occur: what is the velocity of the wave, and what are the frequency of the wave, and then how long is the material that the wave is going to be traveling on. Now, as you recall before, the velocity of the wave is determined by the medium. The frequency of the wave we'll control with this oscillator, or what I like to call a wiggler. Now, there are various standing waves that we can generate. These various standing waves are called harmonics. The first harmonic is a very simple harmonic. It's just one big hump oscillating up and down. It's what you see when you pluck a rubber band, and it's also what you hear when you pluck a wine glass. Ah, that's nice. That first harmonic is sometimes called the fundamental frequency or the natural resonance. It's what everything oscillates by whenever you flick it or pluck it. It's what that string will naturally want to oscillate to. So no matter how hard I flick the wine glass, it will always generate the same note because that's its natural resonance, its fundamental resonance, or its fundamental frequency. Now, looking at that fundamental frequency, to get a full wavelength, I've got to go one full peak and then one full trough. So this standing wave's wavelength is actually twice the length of the string. Now, velocity is frequency times wavelength. So if we know the velocity of the wave, we now know the wavelength, we can figure out what frequency we need to actually get this standing wave. And we can do this for various harmonics. So the second harmonic is adding another hump to our wave. So now we have two humps going across, and they kind of oscillate back and forth. Well, now a full wavelength is just one length of the string. One across gives us one full peak and then one full trough. If the string is the same, then the velocity is the same. And so now we can look at how does that change the frequency to get that particular standing wave. And we can do this for the third, the fourth, and the fifth, on and on and on, adding more and more harmonics. The higher the harmonic we go, the more wave we are cramming onto that same length of string. And in order to do that, we have to keep increasing the frequency of that oscillator or the wiggler. The velocity is determined by the medium, and then the wavelength is just determined by how much wave we've crammed inside that string. And it doesn't just work with string. You can generate a standing wave with air. So think about the column of air inside here, and I'm going to blow across the top. We get a particular note. that air is oscillating back and forth inside. It wants to get out because I've made a low pressure system, but as it tries to get out, you have another low pressure system down here, and that air moves up and down kind of like a mass oscillating on a spring. It's generating a standing wave. Now, if I change the length of the air column, it's hard to see, but I've got this filled up halfway with water. So now I've changed how much air can actually oscillate up and down. The less air, the less mass there is, the faster it can oscillate. And the faster it can oscillate, the higher the frequency of sound that we can get. Now, standing waves are crucial for instruments and generating sound, which is what we're going to look into next. How does sound interact with your ear, and how is the properties of waves of sound different or the same compared to other waves? We'll see you here next time, and as always, keep learning.